好的，今天呢，我和大家分享一下一篇跨模态的文章 Cross-Model Retrieval Using Deep Decoordinated Subspace Ranking Hashing。我们一起来读一下这篇文章。这篇文章呢是由University of Central Florida Kevin 和 University of Central Florida 凯利 University of Central Florida King 三位作者。Abstract 我们已经我之前有读过，它主要讲什么呢？讲 cross-model hashing has become a popular search topic. In this paper, we propose a novel deep learning architecture called Deep Decoordinated Subspace Ranking Hashing. It's kind of deep decoordinated subspace ranking hashing that use features ranking methods to determine the hash codes for the image and the text modalities in a common Hamming space. Specifically, DDSRH learns a set of decoordinated nonlinear subspaces on which to project the original features so that the hash code can be determined by the relative ordering of project features values in a given optimized subspace. The network relies upon a pre-trained deep feature learning network for each modality and a hashing network responsible for optimizing the hash codes based on the known similarity of the training image text pairs. Our proposed method includes both architecture and mathematical techniques designed specifically for ranking-based hashing in order to achieve decoordination between the bits. So it's kind of decoordination between the bits, bit balancing and quantization. Finally, through extensive experiment studies and towards use multimodal dataset, we show that the combination of those techniques can choose state of art. Indeed, this kind of thing is not state of art. I have found some other articles which shows excellent performance than this. Now let's go to the introduction part. The prevalence of digital and social media, blah blah blah, just skip it. The K-linear label problem is a classic problem that involves retrieving the K database items that are most similar to the query. The main issue with KNN is the high computation cost that can be attributed to the curse of dimensionality. So especially when dealing with multimedia such as high-dimensional images and videos, in order to avoid making costly comparisons among examples in the original feature space, hashing for similarity search has become a popular dimensionality reduction technique. Through hashing, examples can be compared much more efficiently in a discrete Hamming space of much narrower dimensionality. So for this paragraph, it talks about the questions about the k-nearest neighbors search. Usually, if you want to do the match between two modalities such as face, such as images, such as the text, you need to do the Euclidean distance match, and this can be time costing. And the locality sensitive hashing, LSH, introduced the concept of hashing for similarity searching. Initially, methods in the LSH family relied on choosing random hyperplanes to separate the data points, where each hyperplane accounts for one hash bit, and the hash bit is determined according to which side of the hyperplane the data point belongs. Local sensitive hashing is an example of data-independent hashing method, since the hash function depends on randomization rather than the actual data. Data-dependent hashing methods are now the more common variety. Those methods use either supervised or unsupervised learning algorithms to learn meaningful hash functions that are tailored to the data. The problem of cross-model retrieval is especially complex, because it requires the comparison of two objects that exist in entirely different feature spaces. Thus, cross-model Hessian solutions must either determine an effective mapping from one modality to the other modalities, of a mapping from each modality to a common Hamming space. In this work, we focus on later approach, so we're going to mapping from one modality to the other modalities of a mapping from each modality to a common Hamming space. So this is our goal. It's the goal of this paper. Instead, this work is motivated by the ideas introduced in 16, and this paper is also published by the author Kani, alright? And linear subspace ranking hashing coexisting. The idea is to learn a unique k-dimensional linear subspace for each hash bit, such that we may generate a key array hash code. To determine each hash bit, the original data point is projected onto the corresponding k-dimensional subspace, and the hash bit is set equal to the index of the dimension with the maximum projection. Although it has achieved a competitive performance on a number of cross-model retrieval benchmarks, there are several limitations that need to be addressed. First, the use of strictly linear subspace presents the optimality that may be achieved by exploiting the non-linearities of deep neural networks. Second, there is no explicit way for LSRH to make sure that multiple hash bits are uncorrelated. Third, the hash codes generated by are not balanced, which can cause an underutilization of the available information capacity of 8-bit hash code. Finally, LSRH has no unified method for feature representation across modalities of datasets. The use of handcraft features undermines the generalization or generalizability of the model and neglects the potential of supervised deep learning for feature representation that has proved to be powerful in many recent hierarchical deep learning methods. So they have problems for the old LSRH. The first one is the use of strictly linear subspace prevents the optimality that may be achieved by exploiting the non-linearities of deep neural networks. Second, how to understand this? The use of strictly linear subspace prevents the optimality that may be achieved by exploiting the non-linearities of deep neural. So previously they used the linear subspace, but indeed maybe they have some non-linearities. Maybe it's best of it can be the optimized one to achieve. So there is some options to improve. The second one is there is no explicit way for LSRH to make sure that multiple hash bits are uncorrelated. So if the bits are correlated together, and then this is kind of information redundancy, so you can they rely on boosting to implicitly reduce the code redundancy. Third, the hash code generated by LSRH are not balanced, which can cause an underutilization of the available information capacity of 8-bit hash code. Finally, LSRH has no unified method for feature representation across modalities of datasets. So the use of handcraft features undermines the generalizability of the model and neglects the potential of supervised deep learning for feature representation that has proved to be powerful in many recent deep learning methods. So in this paper, the author introduced a novel deep neural network architectures for cross-model hashing called deep decorrelated subspace ranking hashing that addresses the above limitations. First, by making use of deep neural networks, DDSRH is able to learn ranking subspace that are more optimal due to their non-linearity. We address correlation between the bits, that is bit redundancy, by abandoning the typical full connected model in favor of full connected sublayers, with one sublayers for each key rehashing bit. Next, we counter the effects of unbalanced bit distributions by introducing a regularization term designed to encourage bit balance. A second regularization term is also added to improve the quantization performance of the model, which actually competes with the bit balance term in effort to achieve an optimal balance of the terms. Finally, we create a unified feature representation by employing pre-trained image and text feature extractors to precede the hash network and feed it with meaningful features that have benefit from supervised deep learning. In this paper, we describe each of the information components in detail and evaluate the effectiveness of each technique by using each one in isolation and in combination with the others. We show that the overall model not only greatly outperforms LSRH, but furthermore achieves state-of-the-art results and two widely used datasets for cross-model retrieval. In summary, the major contributions of this paper are as follows. So the following would be the contributions. We propose a novel deep neural network architecture that is the first to use decorrelate nonlinear subspace ranking hashing for cross-model retrieval. We introduce novel decorrelation, bit balancing, and quantization techniques that are specifically designed for hashing using subspace ranking and evaluating the performance gains obtained by using each technique. We demonstrate through several experiments that DDSRH obtains state-of-the-art performance and to widely used dataset for each. So here I should say this is not state-of-the-art. Let's add some. So the first, the performance is not state of art because I already found some papers such as, let me find the paper name. No. Oh, yeah, this one. Such as this one. Okay. Oh no. Never mind. This. And second thing, the performance in this paper, I think, will depend on the feature extractor, because the author, this is the unit, I think they use some unified feature representation. Okay. The remainder of the paper is organized of the following manner. Section 2 discusses network, includes both linear and nonlinear cross-model hash methods. Section 3 describes our method in detail. And section 4 discuss the experiment's results. Section 5 concludes the work. Related work. Let's read some part of the literature review. I think this paper is really short, so we can take some time to read. The earliest work on cross-modal hashing was cross-modal similarity-sensitive hashing, which used boosting to sequentially learn linear hash functions for each modality. So this is the first one to use the boosting method to learn. Other early cross-modal hashing methods include cross-view hashing and code recognition hashing. Since those pioneer works, cross-modal hashing research has been into several directions, summarized here. Some methods include collective matrix factorization hash function. So this is a function I showed you just now. It's kind of matrix factorization label consistent hashing for large scale cross-modal similarity search. So it also is this kind of CMFH. And latent semantic sparse hashing use matrix factorization method to learn hash codes. So this is one. Other methods were designed with scalability considerations at the forefront, including intermediate hashing, semantic correlation maximization, and semantic topic multimodal hashing, quantized correlation hashing, and composition blah blah blah. Okay. An emerging category of cross-modality hashing algorithm uses a two-stage learning framework that separates binary code learning from hash function learning. In the first stage, the binary code for each training instance are discretely optimized by minimizing and loss function based on the similarity of the instance. In the second stage, the hash functions are learned for each modality by treating each of the optimized bits as a classification problem. Semantics. So for the second stage, usually you add the boosting technique. Semantics preserving hashing is a well-known approach that first learns the hash codes by minimizing the key divergence between the cross-modal similarity distribution and the hash code distribution. SCPH then uses logistic regression to learn the hash functions for each modality. Label preserving multimedia hashing uses a general loss function and optimization and optional bit balancing term to be used for the hashing code learning, and makes use of positive decision trees for the hash function learn stage. Semantic label graph hashing introduces a semantic label graph to get the hash code learned by introducing a fine-grained similarity matrix based on the neighborhood structure of the graph and the semantic similarity of the instance. Another increasingly popular direction for cross-modal hashing algorithm involves deep learning. This is about deep learning, and Mathis was the first to use pernicious neural networks for cross-modal hashing. The general structure involves one neural network for the text modality and a pernicious network for the image modality has been imitated and modified by more recent works, including the proposed TDS arch. Of those similar works, deep cross-modal hashing was the first method to use deep neural networks to learn features and hash codes simultaneously. During each training iteration, similar image text pairs are given the same hash code, where just the image of the text feature parameters are learned. In the third step of each iteration, the image and text feature parameters are held constant while the hash codes are learned. Correlation hashing network was the first network to consider cosine max margin loss for deep hash methods, as well as quantization max margin loss, which acts as a regularizer rather than learning feature and hash code simultaneously. CHN pre-train an image feature extractor and a text feature extractor, both of which become components of the final model. Our proposed method follows this same approach. Okay, so that means their method have a feature extractor and a text feature extractor, and the two extractors are part of the approach. Connective deep quantization is the successor to CHN. The main difference is the use of connective quantization codebook that is shared across modalities, which was sent to improve the quantizability of the deep representation and the quantity of the resulting hash codes. One drawback of all the aforementioned methods is that they are all dependent on exact feature values, which makes them arguably more susceptible to noise and variations. By contrast, all methods belong to a relatively new class of hash function based on ranking operations, which are closely related to rank coordination methods. Though techniques in particular are known to be robust against noise variations, even so, ranking-based hashing for cross-model retrieval remains a very understudied area. Linear subspace ranking instead of a winner-take-all hashing and mean-wise hashing. So this is inspired by it. Correspond to the maximum feature dimension for each feature subspace, rather than use randomized subspace in the original feature space like WT and mean hash, not to optimize subspace in a new phase, blah blah blah. In summary, okay. So this is the section 3, deep decoordinated subspace ranking hashing problem definition. So this is modality X and modality Y, and dx dimension image, blah blah blah. Also define X with the set of similarity tables. So we're going to here ranking based hashing. I will leave this out because I already know this. If you want to know more about this, I can give you a quick explain. So the dx is the modality X, dy is modality Y, and S is the similarity matrix, and this is hash functions. So the objective is try to minimize the error between them. Let's go to the ranking based hashing. So this is the introduce about the ranking based hashing. What we are going to do is to find out this H is the hash function, and this is parameter, and J is the input sample text of image, and we input the J, and we have a projection matrix W, and we try to find out the argument of hash function who makes this the biggest one, the max. This is subject to 0, 1, and 1 th equals 1. Oh, sorry, H is not hash function. From 1, note that both natively I use linear embedding functions for this, but DDSIH instead use a nonlinear embedding function that can be used to reveal more discrete linear ranking structures that cannot be exposed in linear subspace. We accomplish this by designing a deep neural network architecture to learn the nonlinear ranking subspace, such as designers to take advantage of both ranking correlation method and deep learning to learn the most ranking based hash functions. DDSIH also makes use of novel decoordination, bit balance, and quantization approaches that are designed specifically for the key area code scheme in the subspace ranking problem. And comparison does not consider bit balancing, quantization loss, and has to rely upon boosting for bit decoordination rather than explicit bit decoordination, which is made possible. Okay, so this is in the following subsection, we introduce the objective function and its components, which are responsible for ensuring cross-model similarity, bit balancing, and quantization. We leave bit declination to section 3.8 because it's a architecture modification rather than a term in the objective function. Objective function. So let's go to the objective function. Objective function has three components: a cross-model similarity loss, a bit balancing term, and a quantization loss term. So they have three components. Cross-model similarity loss term, this is easy to understand. Bit balancing, as the author proposed in the introduction section, and the quantization loss term. So what is cross-model similarity loss? Cross-model similarity is kind of this. The Bix Bjy belongs to 0, 1 arcade, and this is, I think it's the hash code, and the Sij, the similarity matrix. So this is a loss function. So it kind of, you use this kind of representation, the equation, to show the loss term for a single training pair as this one. So there are the vectorized hash codes for image x and text y respectively, and the h denotes hash for images and the h for text respectively. Note that although the length of the hash code is represented as L times k bits only for mathematical convenience, the actual binary code length is only L multiply log 2k. We can interpret 2 as follows. First, it is easy to see that the result of the subtraction operation is as scalar between -1 and 1 due to the constraints placed on h in 1. If the image text pair are similar, we will make the result of b, this part to be very close to L, so that the loss gains to 0. For this to occur, the position of the 1 values in B and B should be the same. That means that the 0 and the 1 would collision together, indicating agreement as the indices of the maximal embedding feature dimensions across modalities. Otherwise, if the image text pair is similar, we will make the result of B very close to 0, indicating a difference in the position of 1. Ultimately, this criteria accomplishes the goal of pushing the hash codes for similarity image text pairs close together and pulling the hash codes of dissimilar image text pairs far apart. The overall similarity of loss term S is the aggregate similarity loss for all Sij belongs to S and is given as follows. So this is the cross-model similarity and the bit balancer. In addition to the similarity term S, we will introduce the bit balancer term B to balance the distribution of the key digits in the hash code and thus prevent underutilization of the information capacity of the code. Since most hashing algorithms deal with binary codes, they need only to balance the occurrence of 1 and 0 in the code. Thus, one can achieve balance simply by minimizing B1, where B belongs to -1 and 1 is the matrix of binary codes, and 1 is a vector of ones of size n. Binary codes are actually a special case for our algorithm, which must attempt to balance the occurrence of all in a k-array hash code. Then, for each bit position in the hash code, we would like each d to occur roughly times across an instance. We can achieve this by minimizing the following equation, the formula. The balance wx wy equals wx, so this one plus this one, where b is 0, 1, y is a vector of ones of size a, and ones is a vector of ones of size k. For further explanation, let's say equals b times 1. Let's say I count the number of occurrence of the k-array digit d equals I mod k in bit position across all instances. So they also use this kind of evaluation equation of formula to show the bit balance performance. Quantization for binary hash functions. Quantization loss terms aim to achieve a maximal margin between instance classification and user set of the threshold value. Given the classical hash function, a good quantizer would encourage WTX to be far from 0 to minimize risk of similar instance being as user set of the threshold value and obtaining different hash codes. Of course, our algorithm does not use a threshold value to quantize the bits. To minimize the risk of similar instance being an user set of the threshold value. Of course, we are not going to use the threshold value. Rather, each hash code bit is assigned by using the argmax function to over key values. Accordingly, our quantization loss term aims to maximize the gap between the maximum value and the other k-1 values. Note that although the implementation of our quantization loss term differs from the classical binary threshold case, the motivation is the same: wish to minimize the risk of similar instance obtaining different bit values by a narrow margin. We will also minimize the risk of these similar instance obtaining the same bit values by a narrow margin. Because the formal equation is best explained after the network structure has been introduced, in fact, we simply refer to the quantization loss term as quantization WXWY is the form given in 7. So, overall objective, we're going to the 7. So this is a quantization equation. Okay. So we have an overall objective function is the similarity loss, balancer, and the quantization. S is the similarity loss term defined in 3, B is the bit balance term defined in 4, Q is the quantization loss term to be defined in 7, and alpha hyperparameters of the algorithm. The point section described. Okay. So the quantization, what is the really reason why we introduce the quantization? So I think the author did not give enough plan to explain why quantization is needed here, and why just here. Okay. Optimization. So that unfortunately due to the discontinuous and the non-convex nature, so this kind of part is similar to the other kind of people like this. It's non-convex and you need to do the optimization, but that optimization I think it's similar as others. Optimizes the embedding output by the neural network by combining the proposed similarity in bit balance terms with no adaptations of decoordination, quantization for subscript, blah blah blah, describing the following sections. Okay. Network architecture. A deep neural network consists of 2 independently pre-trained feature learning network, one for each modality, followed by a hashing segment and connected by a cross-modal node segment. A description of full network during the cross-modal training is given in figure 1. And so, feature learning segment. So let's go through the title, the section, feature learning segment, hash segment, and training the network. And we have the experiment and data set and the result comparison. Okay. So we are going to read this figure. So we have feature learning segment, the hash segment, and loss segment. So for the feature learning segment, we have image networking and text networking. So they use AnnexNet to extract the features, and use the features. They go to input the features into the hash segment. And this is text network. They use this kind of network to extract the features, and they input the next network into the next section. So you can see here, this may be the convolution network they use. It's the architecture, and text network they don't provide any details. So we can see the output is 4096, and this is the hash segment. They input the hashing, and then they divided it into equally sized groups, and calculate. So this is a loss segment. This is inner product loss function. Image text similarity 1 of 0. So let's go into this. The network consists of 3 segments: feature learning, the hash segment, and loss segment. Input to the network are given by the white arrows, where solid black arrows indicate fully connected layers of groups. Layers are given a label and a dimension. The softmax function is given by data. So this is soft function, and it is applied to groups of neurons of size k. Neuron values are depicted in grayscale. Neuron values are depicted in grayscale, with black indicating low values and white indicating high values relative to the group. Assuming the first neuron in each group is at index 0, the corresponding hash code for both the image and the text would be the quaternary code 21. Really? Okay. So this is the network they use. So this is the hash segment, and we see the experiment. Dataset uses MAR flicker, known as white, and trim pairs. How they generate the trim pairs? Trim pairs for the single modality classifier pre-training phase. All image and text except those that exist in a query set or orientation set are used for training. So during the cross-modeling training phase, a trim pair consists of any one image and any one text from training set. The similar training pairs are chosen at random by choosing pairs of image text that shape no class labels. Rather than choosing the similar training pairs at random, we employ a similarity threshold function that is based on the following notation. Similar training pairs whose image and text components share multiple class labels are more likely to be useful for training the network than similar pairs that share only one or too many class labels. So we choose the similar training pairs by using the following similarity threshold function. Okay, so they propose a new method to choose the training samples. So they choose the labels with more instead of the comparison with baselines. So as we can see, we don't need to read those text. We just read this table. As you can see in the table, they claim they are the best. Of course they are best, otherwise they cannot get this publication done. So they are the best one. And we can see the precision record corps use 32-bit hash code. DDSRH outperforms the baselines in all cases. So I think this is the right line supposed to be the method here. Okay. Evaluation study to evaluate the effectiveness of the decorrelation, quantization, and bit balance components of a method. We run several experiments in which each component was either utilized or not utilized. To eliminate the bit balance of quantization components, we simply set half on upline in 5 to 0 respectively. To eliminate the decorrelation components, we modify the neural network architecture such that H1 and H2 in figure 1 are fully connected. The experiment ran using a hash code length of 32 bits. The MP and 50 result of this experiment are shown in figure 3. So we see so decorrelation, bit balancing, and quantization. So DBQ, so only with D. So D and B, DBQ. So this one means nothing. They have an. So what is the difference? Suggest that if they have it seems there is no difference. For this one, DB or DBQ is the best one. Okay. Does not consistently improve the MVP result. We believe that this is because the simulation loss time from 3 can only be truly minimized, such that no quantization loss would occur. Thus, even though the similarity loss term is designed to enforce similarity learning, it appears to be sufficient enough for quantization. Here, note that the results shown in figure 2 and table 1 are gathered using decorrelation, bit balancing, and quantization. However, as can be seen from figure 3, similar results can be achieved by setting number in 5 to 0 and effectively removing blah blah blah. So its DBQ would be the highest one, but for this one, no. DBQ, nothing. B and BQ. Conclusion. In this paper, we have proposed a novel ranking-based cross-model hashing method called deep decoordinating subspace ranking hashing, the first of its kind of exploiting decoordinated linear ranking hashing for cross-model retrieval. The nonlinear decoordinated subspace non-repetitive network proved to be much more effective at preserving the cross-model similarity than the linear subspace proposed in PROX. Additionally, we have proposed adaptations of decoordination, bit balancing, and quantization for ranking-based hashing, and we have demonstrated that the decoordination and bit balancing in particular can significantly improve the performance of the model. Comparing DDSR to several model baseline, we have shown that the DDSR significantly outperforms current state-of-the-art methods and the text query image tasks, while achieving competitive of superior performance as the image query tasks. So that's today's share of this research paper. Thanks so much. Bye.